area is created. The fracture surface energy required for this comes for the strain energy stored in the material, which could further come from the work done by externally applied load. In ductile material, energy is also extended for plastic deformation at the crack tip. A crack reduces the stiffness of the material or the structure. So this is a crack size 2A, and crack is a local stress amplifier sense rather than a global weakener by decreasing the load bearing area or the load bearing capacity of the structure. Characteristics of crack. Cracks can be characterized looking into the following aspects. It connects with the external free surface, completely internal. Internal cracks which connects to outer surface, and surface cracks. So crack with some contact with external surface are exposed to outer media and hence may prone to oxidation and corrosion. So crack lengths, the deleterious effect of the crack further depend on the type of crack. That crack first, second, or third, as shown here, completely internal crack with connection to the outer surface, or surface crack. Okay, crack tip radius. This the shaper or the sharper the crack, the more deleterious it is. Crack tip radius is dependent of the type of loading and the ductility of the material. And the third one is the crack orientation. With respect to the geometry and the loading, we will see more modes of the loading in the this context soon. Okay, actually this is the crack length, and crack tip radius is here. The radius is here. Okay, this is the crack situation. Mode of the formation of cracked body, or modes of fracture we can call. In general, we have three modes of loading of cracked body can be considered, which are called the modes of deformation, or that is the first mode, second mode, and the third mode. The first mode is called opening mode. Okay, it is opening mode. The second mode is sliding mode. We can easily see from the picture. This is opening. It makes the crack to open this and this side, or we can see this and this side. Then the crack will open. In this case, sliding mode. This pushes this direction and this pulls in this direction. So the two materials will slide to each other. And here it makes kind of tearing or scissor effect. This is a scissor effect. So that is third mode. In the general case, for the crack in an arbitrary shaped body under an arbitrary loading, the mode is not pure. It is mixed mode will be there. Okay. So modes of deformation are given like this. Okay. The loading specified and the geometry of the specimen illustrated for mode 2 and 3 above do not give rise to pure mode 2 and the pure mode 3 deformation. Others constraints or body shapes are required. Important points in fracture. One of the goals of fracture mechanics is to derive the material property, the fracture toughness, which can characterize the mechanical behavior of the material with flaws or cracks in it. Fracture can broadly be classified into brittle and ductile fracture. This is usually done using in the macroscopic ductility observed and usually not taking into account the microscopically plasticity, which should be significant. So ductile materials is one which yields before fracture. Further, one would like to avoid the brittle fracture, wherein the crack propagation leading to failure occur with very little absorption of energy. In brittle fracture, the crack may grow unstable without much predictability. Three factors uh, have a profound influence on the nature of fracture. One is temperature, second is the strain rate, and the third one is the state of stress. Okay, so materials which behave a brittle fashion at low temperature may become ductile at high temperature. When a strain rate is increased by a few order of magnitude, a ductility of material, ductile material may start to behave in a brittle fashion. So that is the three factors, the correlation. So ductile material sigma yield is less than to sigma of failure. Okay, so fractures, ductile and brittle, that is classified into two. And the brittle fracture promoted by the three factors uh, that profound the influence of nature of fracture. These are low temperature, high strain rate, uh, triaxial state of stress. This brittle fracture profound by again fracture affecting factors affecting fracture. This temperature, strain rate, and state of stress, which is specified here. High strain rate and low temperature essentially have similar effect of not allowing thermally activated motion of dislocations. That is not helping plastic deformation by sleep. And in specific case, some of the sleep systems being active at high temperature may become inactive at low temperature. Okay. So by triaxial state of stress, we mean tensile stress of the same sign along Y and Z also. And the triaxial state of stress does not promote crack propagation, but suppress the plastic deformation. Since the plastic deformation is suppressed, the crack tip remains sharp, this promoting brittle fracture. So far, for the plastic deformation, the following orders is better. Triaxial is less important than biaxial, and the biaxial is less important than uniaxial. So the uniaxial is the best one. Okay, this is triaxial. Stress in X, Y, and Z. Stress in X and Y, and the stress in X. Or we can call it as it is local orientation, sigma 1, sigma 2, and sigma 3 for triaxial case. For biaxial case, sigma 1 and sigma 2. And in the uniaxial case, sigma 1 is so the worst scenario is in the triaxial case, and the best scenario to avoid brittle fracture, uniaxial test is preferable. Fractography. Considerable amount of information can be gathered regarding the origin and nature of fracture by studying the fracture surface. In fatigue failure, for instance, we can know the place of origin of the crack, stable crack propagation regions, etc. The fracture surface has to be maintained in the pristine material that and the oxidation, contact damage, etc. should be avoided to get meaningful information from fractography. It should be noted that a sample which shows very little macroscopic ductility may display microscopic ductility. as can be seen in the fractograph. We can see here a result of fractography. So a truly brittle sample shows faceted cleavage planes. We have cleavage planes here. Okay, these are the faceted cleavage planes. Okay, while ductile fracture surface display a dimpled appearance. Okay, so a scanning electron microscope, fracture surface by scanning electron microscope can be shown in this picture. Classification of fracture. Okay, fracture can be classified based on the crystallographic mode, appearance of the fracture surface, strain to fracture, and crack pass, and also other factors also there. Okay, so presence of chemical species at the crack tip can lead to produce fracture stress and enhance crack propagation. Presence of brittle phase along the grain boundaries. Okay, for Fe3C along grain boundary in steel, glassy phase at the grain boundary in Si3N4 ceramics can lead to intergranular crack propagation. This preferred weak pass along grain boundaries implies low energy expenditure during the fracture, that is low fracture toughness. So we can see here there is a transition. These are grain 1 and grain 2 is there. There is also a transition here. Okay, so this is the weak pass along grain boundary. Okay, and there are brittle cementite along grain boundary along the which crack can propagate are presented here. Okay. So the behavior described and term. So crystallographic mode, we can see shear mode and cleavage mode. If that shear mode or ductile and cleavage mode or brittle, appearance of fracture surface, fibrous and granular or bright, strain to fracture, that is ductile and brittle, pass transgranular, that is crack propagates through the grains, and intergranular pass, that is crack propagates through the grain boundaries. Okay, so these are type of failure in uniaxial tensile tension or tension tests. One is the cleavage plane. So for the brittle fracture, little or no deformation observed in single crystals and polycrystalline have been observed in the BCC and HCP metals, but not in FCC metals. Here we can see the slip plane, that is shear mode. Here the fracture is a shear type of fracture failure. So shear fracture of ductile single crystal, no observed in polycrystalline. And here it is rupture mode. So completely ductile fracture of polycrystals, very ductile metals like gold and lead neck down to a point and fade. Here technically there is no fracture. There is not enough material left to support the load. Another is ductile fracture. There is a neck formation here. And then finally, cup and cone fracture is formed here after the nail. So ductile fracture of usually polycrystals, cup and cone fracture. Cracks may nucleate at the second phase particles or void deformation at the matrix particle interface. So these are some contributors who have been involved in the